Hello and welcome. This is a video explaining my self-driving car project. So first up, my name's Finn. I'm extremely interested in machine learning, computer programming, that kind of thing. And I decided to tackle the problem of self-driving cars with a twist though, and to introduce a video game mechanic into self-driving cars and how we can actually use video games to make self-driving cars safer and train them quicker to make them even safer for the roads of today. So first up, before we even get into the details of this project, I want to go over some simple terminology that will be used recurringly in this video and throughout my documentation. So first up, Opencv. So if you're unfamiliar, this is great to get started. Opencv is an image processing library. Think of it like an advanced Photoshop, but we can use it through command lines. So with Opencv, it's very important for machine learning and for self-driving cars. If we see a sign on an angle, for example, we can use Opencv to distort that image to bring the perspective of the camera front on, to make it easier for our sign recognition system to read and correctly identify that sign. So Opencv also has image processing and allows us to put filters over images. And one example of this might be we're looking at a set of lines on the road. We don't care about the colors of the tree, that kind of stuff, so we might use Opencv to grayscale that image, making it easier for the model. We might put another filter called Gaussian blur over that image that extracts some other features. And we then use these features in our machine learning model. And Opencv allows us to do all of these transformations of this image. Next up, Tensorflow, which is going to be a key part of this project. So Tensorflow is the actual machine learning library developed by Google. We will be oscillating between TensorFlow version 2 and TensorFlow version 1. So all you need to know about TensorFlow is it's a library that provides machine learning capabilities to our computers at home. And the basics of machine learning is that you train it to do something. In this case, we might train it to recognize different types of cars, and then you give it a car and ask it what it is. And the machine, if it's trained correctly, the machine model might say that's a car. Or if you've trained it incorrectly, or the image has some other features in it, it might guess that it's something else. In that case, we need to go back and retrain our TensorFlow model. So TensorFlow, machine learning, that's the package that we use for all our machine learning. Second, Keras. So Keras is really useful for storing and applying and saving our machine learning models. So after we put our model through TensorFlow, we obviously don't want to train it every time we want to go and recognize some cars, right? Training takes lots of time, takes lots of CPU power. Therefore, it's not ergonomic and not viable to do this training process every time we want to apply this. So Keras helps us to save this artificial model in a way, saves it onto our hard drive, and next time we want to recognize something, we can take the saved Keras model and implement it into our code. And the Keras model, or the library Keras, allows us to do that effectively, easily. Python is basically just another programming language, like you might have heard, like C++ and C#. Python is simpler to use, but has all the functionality of a higher level language, such as C++ and all of those things. So Python is going to be the primary language that we use throughout my project and this project. So very easy. It's easy for human readable. So if you read a piece of the Python code, it's easy to interpret. And it's not that cryptic heavy like C++ might be, where you don't have any idea of what that line of code does. So really awesome. And finally, I want to talk about the definition of a neural network. So this hooks into our TensorFlow. TensorFlow being the package that does all that machine learning. Neural network is a type of machine learning. It's extremely interesting and extremely powerful as well. So what we've done is basically we've mimicked how the brain works. We have an input node where you put information in. We have a set of neurons with nodes connecting them. You can also have stacked neural network, so with multiple layers. For this example, let's keep it simple. We have one input node, 4 neurons, and an output node. And the weights that are connecting, or the connections that are connecting the input node to the neuron have weights assigned to them. These weights determine how heavily the information is weighed onto that node. So for this project, we're going to basically use a couple of neural networks and convolutional neural networks as well. Don't really need to know what that means. It's a bit complicated, but the basics of neural networks mimics a human brain, has weights that identifies how heavy an input should be recognized or how heavy a data point should be valued in the real world. So that's very simple. Anyway, let's get back into it. So at the moment, I have a lane detection system working, which recognizes the lanes on the road. Very awesome. The second thing we're working on at the moment is vehicle detection. So we obviously want to know when a vehicle is there and when a vehicle is not there, where that vehicle is. And then third, we need to work on traffic light recognition and sign recognition. So that means we can take our video and extract all of these details, lane lines, traffic lights, cars, all of that details out from the original video. So in Forza, there's lots of details. There's lots of houses, lots of trees, and lots of colors. There's a beach, for example. So we don't care about that. The neural network will get confused by too much data. It's called an overfitting problem. So if you overfit the network with too much data and too much information, it will get, in a sense, distracted by what's really important and what's not. So therefore, I want to try and extrapolate all of the important information, such as all those lane lines, other cars, from the original network, from the original video, and use a blank screen with all of this data on that screen as a data input for this neural network. That's the plan, at least. At the moment, stage 1 is just to extract all of that data from the video. So let's get back into it. So let's first have a look at advanced lane detection. So this is a Jupyter Notebook where we can easily go through our Python code in what's called segments or blocks, where we can make sure that that part of the code runs and then we can move on, as well as add debugging information and that sort of thing. So it makes it really easy for newcomers to Python to access this kind of material and to really understand what they're going through. And by the way, if you want to install this Python notebook and all the packages that we previously talked about, there's a link on my GitHub that downloads a bash file that will install all the relevant programs needed to run all of these programs. So first up, how do we run Jupyter Notebook? So to run Jupyter Notebook, head over to your terminal and simply type in, after you've installed that bash file that installs Jupyter Notebook, you simply launch it with typing Jupyter Notebook in your selected directory, hit enter, and that one will launch up like so. Really easy to use. So let's jump back into it. So this is advanced lane detection with a sliding window approach. So here we can see we're importing CV2, which is Opencv, the package that we previously talked about, and Pickle, which is very similar to Keras, which is a data management package as well. So let's hit run on that one, make sure we have no problems. Awesome, number 1. So because this program is written for a real camera to take images, we have distortion on the sides of these images. So that's why we're importing calibration images, so that we can create a calibration profile that we then apply to our image later on to, in a way, calibrate it to make it work for Opencv as best as possible. So let's give that one a run as well. All good, no errors, and we can tell if Python is doing something by this kind of kernel indicator there. So we are just calibrating images. So this is our original image from Forza Horizon, and this is our undistorted image. So as we can see, Opencv has applied a fisheye lens. So these are useful functions that we are just defining, and these are all the filters that we saw previously. So here, this is the definition of a Sobel threshold filter. which means when we call in our function do a Sobel filter on this image, the program Python will actually go through here and carry out these instructions. The same with mag threshold. We're just defining that these instructions mean mag threshold. So let's give that one a run. No problems. Awesome. And just to visualize it, so a grand X filter would look like this on our image, grand Y filter, and this is a mag threshold. So what we're kind of doing, we're kind of testing a range of filters to see what ones kind of work best. And then, so as we can see, S binary didn't do us any good in this filter, in this scenario, which brings us to our processed image. And this is kind of creating a pipeline for what process image means. We can give it an image, in this case UTest, and this is kind of telling us, okay, we're taking one of the grand X filters, one of the grand Y filters, a C binary filter, and that all equals up to 255, which is the maximum value of an image. And which means this is our final image after all of those filters that we just applied. So let's go through. So now we're reading the test images and pushing them through our pipeline, which is that process image pipeline. And here we're applying Grandy X, C binary, and defining that that means this is the processed image. And these are values that we can change and values that you have to perfect to make the system work as intended. And these are the values that I found to work the best with my Forza Horizon video. Because my video was taken from the hood, we get a bit of the hood in the video, as you can see here, and obviously we don't want it, we want to cut that part out, because we don't want to look at the hood or the reflections in the hood. So that's why we've changed these videos. So bottom trim, I've moved it up to 70, that we essentially cut out anything below that threshold there. And this is really interesting. So this is where we do the bird's eye view transformation. So the problem with lane detection on a linear basis, on a forward-facing basis that we see here, is that you can see these lane lines close to the car are very prominent, and they have a good footprint on the image that our filters can pick up. But the further we move away, these pixels and the lane itself gets smaller and smaller, makes it harder and harder to detect. And therefore we kind of grab this this square that we've drawn out here through these four points, and then we're kind of moving our camera using Opencv and matplotlib to give us an overview that gives us a bird's eye view image. So here you can say this is the same point closer to the car, is sort of the same width and has the same impact on the filters that a lane line more far away has. This makes it really easy for forward planning and to get a better resolution of these lane lines further out. And it means that we can not predict, but that we can keep track of the lane lines a bit further out than just really, really close to the car, which is obviously very important for self-driving cars. So here we're applying convolution, and this is where we apply our sliding window approach, as we can see here. So that works really well, and we're detecting all those lines there, working well. So these are just some test images, and if we need to change, so we have those same values that we mentioned up there, and now we have to identify the window width and window height value. These are the values that I found to work the best, 50/80 for my environment and for that Forza video. And the reason that I found these values to work the best was because this model always had trouble with detecting lane lines with the broken lines, where we had space in between two lines, and it would never catch on to the one in front before it lost track of the one in the rear. So by making the window height as high as possible, I was hoping to overcome this issue by increasing the search height, and then therefore increasing the probability of it finding the next lane line before it lost the one before. It still is not polished up, and it still does not work to the best of its ability. I've gotten pretty close though, and I'm still happy with the results, but that gives you kind of an idea of why these values affect the performance of the lane detection system. Passing it through our pre-processed image, and this is our image underdistort function that we mentioned up ahead, where we calibrate the camera to underdistort the image. And let's just move through, and this is where we identify the lane lines. So this is just a black and white where these lane lines are in our image, and then these are those lane line detections on top of the image. So using that, we can actually also calculate where our car sits in between these two lines. And this is the first step where we can introduce steering movement, for example. So reading this, the vehicle is 37 meters left from the center. We could put in an if function to say if car is more than half a meter away from the middle of the line, input steering to the opposite to get it back on track, for example. So that'd be a first thing where we can implement self-driving technology, or lane assist technology, I'd call that. So this is just our function to process the video. So process image, and we're kind of ripping every image from that frame and passing it through this kind of loop. And at the end, we simply define our input image and our output image. That's a quick overview of the Jupyter Notebook Advanced Lane Detection. So it's not that hard, but once you get to know it and once you go through these examples with the images to support it, you do build an understanding of what it's actually doing. And let's next have a look at Yolo and how that kind of works. So before we get into that, let's quickly brainstorm the next step for ourselves for extracting all of these features from a video to get all the relevant information that a self-driving car model could, in theory, use to make practical decisions and, in the end, drive itself. So we have lane detection and lane recognition systems, and those are keeping the lane lines and knowing our boundaries of the road, if you will. We also have a system that could potentially steer our car back into the middle of the lane, so a lane assist feature. We have that as well. But we still don't have enough information about the world around us. We still don't know any about any cars, about traffic signs, traffic lights, about pedestrians, all sorts of things. And that's where Yolo comes in. So after lots of research and lots of trying different systems, the first system I tried was a Hogue detection system that was specialized or was designed to detect vehicles, nothing else, just vehicles. So what I did is I downloaded a huge data set of vehicles and then used something called Hogue detection or a Hogue filter on top, which takes the pixels but it takes the broad outlook and puts it into blocks and then has a gradient on each pixel. And a gradient showing what it might look like. So from this, we basically get a box type image. We have a flat underline for the car, curved or straight boxes up, and then a roof. That's from the back of a car. And to make it as easy as possible and as fast and efficient as possible, we look at these basic features like, okay, we're just looking for a box type shape that looks something like these. And obviously we have thousands of training units, so we have a bit of an understanding, or the Hogue model has a bit of an understanding of what this might look like. It went all right. It didn't detect as well as I would have hoped. And it would have been a bit harder to shoot a video stream through this system. And it was only specialized on detecting cars, nothing else. So I quickly abandoned that pursuit of that type of technology and I went towards something newer, Yolo. So we talked about it previously. Yolo, you only look once system, and this applies our knowledge of convolutional neural networks. And neural networks, as we know before, is simplistic, in a very simplistic manner, of how the brain works. We have input nodes, we have neurons with weights attached to them, and those weights define how that input data is being recognized into that input node, and these weights are what we change throughout the model. And we're gonna shoot our video through that, and YOLO in this instance detected everything from traffic lights to pedestrians to cars to trucks as well. Obviously, in the future, it's going to be very nice to know if we're dealing with a car in front of us or a big truck that might take longer to accelerate, so on and so forth. So it just gives us a lot more depth about the world around us in a self-driving car. And that's primarily why I went with the YOLO system in the first place, or after I looked at Hogue. So that was a really good idea. And YOLO works fantastic. It's a bit slow. I only have a slowish machine with me here, but it has the possibility, it has the potential to work in the real world. And it's not so much the speed that I'm testing, it's more the system and the idea that we can use something like this in a self-driving car. So, how does YOLO work? In a bit more detail than before. So in essence, we have that same system. We have input nodes, we have our neurons with weights attached to them, and then outputs. So what we first do with the frame, we get our frame, we divide it up into what's called an S by S grid. And that's a grid of, could be any width of pixels. Typically it's 16 by 16 pixels, and that is now a mesh, which makes it easier because for our YOLO, because we have so many outputs, so there's so many potentials. So it could be a car, could be so many options. So we have typically lots and lots of input nodes, and we shove all of this data into this input node, or into an array of input nodes. These weights get attached, and we push it through that neural network. And we actually use Pickle, is our pickled network file. And Pickle, as we know from our discussion before, is a system used to store, load, and save neural networks. And that's what we're doing here. So we downloaded the YOLO code, attached our pickle network, or our pickled network, and then we also downloaded a compressed file of all those weights that we download as well, that we then link into our YOLO network as well. So that's roughly how it works. Obviously, it looks a bit more complicated on screen. We have lots more convolutional networks that all work together. We have bounding boxes and a heat map of probability of what might be in that 16 by 16 square. And at the end, every time a bounding box of prediction is overlapped with another bounding box, it adds to the probability of that being correct. So say we have a picture of a dog, and there's lots of bounding boxes. So some boxes are the head, we have the tail, we have the face, so on and so forth. Because all of or the majority, it might seem, of our input nodes recognize this 16 by 16 square that we divided up in our S by S grid is a dog, gives the output more probability of it being right that it is a dog. So we, at the end, clean the image with all of these bounding boxes, and we take the most prominent box and circle that one to isolate the target in its entirety, so that we have the whole dog surrounded instead of just the face or part of the paw, for example. And we do the same with cars. We get lots of cars, and the 16 by 16 S grid might be divided up, and this input node of the neural network might get a tail light, for example. Now, in our data set, we know that this is a part of a car, and we kind of run that through our convolutional neural network and apply bounding boxes to it, and that heightens the probability of the final network deciding and supporting that it is a car. So that's YOLO, and the reason I used it for this project is because it detects everything from cars, trucks, people to pedestrians, even traffic lights, and that will give us a much clearer view of the world around us, as well as it being able to run at a high FPS, a high frames per second, to make it safe to use in a self-driving car. Obviously, we can't have a network that takes a second to process one frame, because the world changes so fast around us if we're in a car. So that has to be very secure, and that has to be pretty on point with how fast this network is able to respond. So bringing together all those different technologies, we have lane detection system that we talked about earlier with Opencv, and YOLO with Tensorflow and Keras models as well. And bringing those two technologies together is really fundamental in our goal to extract as many features and as many self-driving car relevant features from a video stream. So we can successfully detect the lane lines with lane prediction as well, using a bird's eye view approach that gives us a further reach distance into the future as well, where we can kind of predict where these lane lines might be. Paired with Yolo, which gives us car, truck, traffic light detection as well. So we can really map the world around us and figure out if we're in a good place as well. And that could, in the future, allow us to have a system like traffic aware cruise control, where we can actually track the car in front of us and stay a safe distance behind them, for example. It also allows in the future for a full self-driving, where we know the cars around us, we know the lane lines and the lane detection, and then from that we can build on our model to change directions with a goal in mind as well. All of these things are the baseline for this model, or for a full self-driving car that we'll get into hopefully in the future. But this is kind of the first step. Feature extraction from a video stream that we then essentially feed to the future self-driving car model. So the goal from this project was to really prove that we can use a video game as a playground, as a platform to test self-driving car programs and models, and to also test the extraction from a virtual game, a simulation if you will, test the extraction rate so that we can detect cars, traffic lights, things like that, and hopefully potentially use this same model that was trained and you tested in a virtual world could possibly work just as well or even better in the real world. So bringing all that back together, I hope that you've really enjoyed this video and learned a little bit. So this was a deeper dive in the nitty-gritty parts of full self-driving project. We're only focusing on feature extraction, and that is all the features, self-driving car relevant features that we extract from a video to then give to a full self-driving model in the future, but to make sure that this data that we're pulling from our video is really accurate and can be used in the future for a full self-driving model. I hope you enjoy this project just as much as I do. I learned so much about Opencv, about Tensorflow, about self-driving cars, about all these things that we need to look out for, and hopefully all of these experiences and all the things you learned today can really help us to understand how self-driving cars might work in the future for mass transportation and to increase general safety of the roads around us as well. So I will be releasing a third video where we talk about, or where we document my timeline and the problems we had, the errors that we had, and how we overcome those problems as well, through asking questions on GitHub, through general research, through trying a different approach. So look out for that video, that will be an interesting one as well. Anyways, that's all from me tonight.
Cool, let's get to it.